Hi, today I'm going to discuss about tracer balance in the body, the derivation. So consider the mass balance equation. Let's say, let me write it down, tracer balance in the body. Okay, so this is about first order and zeroth order kinetics. So consider, let's say, assuming the tracer you start intake, that's at time 0. And from there, we want to see whether this tracer molecule, how much of these molecules that remain inside the body. So that comes as a concentration. So ingested tracer in the food and passes out of the body, for example, as a urine. So let's apply for the mass balance equation. So that's, remember that the rate of accumulation in the body is influx minus outflux plus the net generation, which is generation minus consumption. So with these, let's say that is a mass. So d dt dm, and right after ingestion, from there, there's no input, 0, minus output. So here comes the assumption. From some of the data, you see the amount of rate of the change looks like the remaining amount. So for example, over time, and this is the amount of mass. Okay, so that's normalized as 100%. Let's say normalize 1.0. So you sometimes see this exponential decay many times. For example, let's say the amount of a nicotine inside the body, then you will see 0.5. This is relative, that will be about 2 hours. What you see here, very interesting thing is when there's a lot left here, then you'll see the rate of decrease is very rapid. However, when there's much less left here, the rate of decrease is much slower. So what that means is the rate of change appears to be proportional to the amount it's left. So for that regard, we can put it as it's proportional to the mass left, and the proportionality constant is a k. So this is a first order kinetics, and assuming there's no new generation and no consumption inside our body. So here, this is an assumption of first order kinetics. Okay, so what that means, the rate change, it seems to be proportional to the amount left in the body. Of course, this is a decrease, so it's eliminating, so that's minus. And also here, we define this k. K is, here is a proportionality constant that we define as a rate constant. Okay, so does it make sense? So here, this is basically the amount of leftover. The ratio is proportional to the mass itself. Of course, this is a decreasing, so it's negative. Then how can we generally solve this equation? So let's get back to this as, let's say this is m sub 0, and when it becomes 0.5 m0, and we define the time as a tau. So we define when by the time this tracer is left half inside the body, the time span there we call half-life, because it becomes half. Okay, so half-life. So does it make sense? So this is now a simple differential equation to solve. So how do we solve this problem? So so 1 becomes dm dt equals minus km. So this is a simple differential equation. You can see whatever to differentiate becomes the same. That is usually an exponential. So mt becomes e to the minus kt, because once it differentiates, minus k came out like here. So the exponent must be minus k here. And then when it comes t equals 0, the original mass become m sub 0. Okay, so for example, then why don't we, based on this half-life definition, why don't we solve this equation? Then when half-life time becomes tau, then m tau should be half of m0. Then you can, from 2, you can see 1/2 m0 equals m0 times e to the minus k tau. So tau can be solved by here 1/k ln 2. So here comes the definition of the relation of tau based on the rate constant k. So you can see this, and also the solution for this equation will be this. Okay, so does it make sense? And however, sometimes you will see rate constant seems to be not changing, and sometimes you see, for example, alcohol case, what you see is like sometimes this linearly decreasing case. For example, a good example is alcohol, ETOH, ethanol consumption. The amount of alcohol seems to decrease like linearly. So in that case, so far, this one is the first order kinetics. So let's say 1 as first order kinetics. So what about second case, which is a 0th order kinetics problem? So that's another. What it means is the rate constant seems to be constant. So the change is constant. So it's not related to the amount of tracer in the body. So in this case, such as time and mass left in the body seems to be just decreasing. So in this is as a 0th order kinetics. What it means is dm dt equals just minus k. So you can solve this differential equation by mt equals minus kt plus constant. And you know the initial condition, which is m0, when time equals 0 is m0, and that becomes the constant. So that you can solve this one as mt equals m0 minus kt. So this is how I think you can solve the equation, and that a good example is alcohol consumption. So what it means is first order kinetics is, let's assume that there's enough of a transformation inside the body. So the more of tracer molecule, the faster we can eliminate in the body. However, the 0th order kinetics, such as alcohol elimination inside the body, it means that if the enzymes to transform this alcohol may be so limited that all the time, even there's more alcohol comes in, the amount of transformation is always the same rate, which means the enzymes are all fully occupied or saturated. In that case, you can observe this 0th order kinetics. While first order kinetics is when there is enough of enzymes, plenty, so that it's proportional to the amount of tracer comes inside our body, we will be able to consume that proportional to the amount of the tracer. I hope this will be helpful. Thank you for your attention.